For the past hours, we already have a look at Thevenin. So next will be looking at Norton theorem. Basically, if you this should be Norton. If you understand what is Thevenin, really get the steps of finding Thevenin equivalent circuit, it's not very hard for you to understand Norton theorem later on. And the difference between Norton and Thevenin is that Norton equivalent circuit, we try to have current in parallel with Norton resistance. So Rn over here should be in parallel with current source. Looking at Thevenin back, okay, looking at Thevenin back, where's the circuit from here? If you look at Thevenin circuit setup, you have voltage in series with resistor. And remembering what we have learned in last class, this kind of circuit arrangement, we can convert or we can transform it into another form, which is current source in parallel with resistor. So in other words, you can always use these two values to convert your circuit to become a Norton equivalent circuit. So here Norton equivalent has current source in parallel with resistor. However, that's not the case at the moment. What we're trying to do here is we try to step by step directly find the Norton equivalent circuit parameters, which is IN and also RN. The steps, I think step number 1 is the same as we seen earlier. We try to remove any load from the network and try to find the Norton resistor looking from that terminal. So step number 1, we try remove the load and mark as open terminal A and B. And step number 2, we try to find Rn, or the value of Norton resistance. Same as we treat finding Thevenin resistance. Here, all voltage sources should be equal to 0. For voltage source, we have short circuit. For current source, we have open circuit. I also put the note over here. Note that the procedure is the same as finding RTH. So in this case, Norton resistance basically is equal to Thevenin resistance, the same value. Except that in step number 3. In step number 3, earlier, when we tried to find Thevenin voltage, we try to find the open circuit voltage at the terminals. For Norton current, IN, what we're trying to do, we try to short circuit the open terminal. Instead, we try to find what is the short circuit current at the open terminal A and B. We done in step number 1. You can use node, you can use mesh, you can use any approach that you prefer. Except that if the question asking about node or mesh, you should follow the question according to the question. For step number 4, once we've found IN and also RN, we need to set up a parallel connected circuit, consists of IN, current source, and also RN as our Norton resistance. And in step number 5, it's basically by putting back the load, we try to find what is the value of current, maybe try to find what is the value of voltage across that load. Okay, we put it this way. We try to learn Norton theorem based on example. This is the first example. we try to find VO using Norton theorem, and try to find IN, Norton current, using mesh analysis. So considering that circuit, first step, you try to remove the load resistor. So since VO is over here, okay, VO is here, means that this is our load. And we try to remove this terminal first. So removing that terminal, we end up with this kind of circuit connection. And to find Rn, what you need to do is you try to set up all sources equal to 0. In this case, we have two voltage sources. So here, voltage source, the first one, 8 volts, basically in short circuit over here. And this 5 volts voltage source is basically under this 2 kilo ohm. This is also short circuit because this is a voltage source. So voltage source, we need to treat it as a short circuit element. And we try to find what is the value of resistance looking from that A and B terminal. Looking here, we have these two resistors in series. You need to combine these two first. Okay, these two should be in series here. And later on, it is in parallel with this 2 kilo ohm resistor. So that's why for Rn, is given by 3 kilo plus 4 kilo connected in series, this one, in parallel with this 2 kilo ohm resistor, 2 kilo ohm resistor. And at the end, you will get the value of your resistor as 1.556 kilo ohm. That's for Rn. For In, you need to find In according to the question using mesh analysis. And according to Norton equivalent procedure, what you need to do, you need to short circuit the terminal. Okay, short circuit this one. You need to short circuit the open terminal. For Rn, you open it up, and for In, you need to short the two terminals that we opened earlier. So try to find what is the current flowing through here, and current flowing through here is considered as our In. Looking at the circuit, it clearly says that if this is mesh number 1, and we denote as we note it as I1, and this is mesh number 2, we denote it as I2, and In is basically the current flowing through here, which is the same current as I2. So it makes our life or it makes our calculation a lot more easier. Okay, now using mesh analysis, what you need to do is first you try to assign your mesh, the current direction of your mesh. Later on, you try to assign the polarity of the voltage drop across each of the resistors of each of elements. Here we have 4 kilo ohm. Polarity should be like this because we consider current is flowing that way. And here we have polarity to be set like this. And at 3 kilo ohm resistor, we have polarity of voltage drop to be set like that. And later on, you try to set up an equation of Kirchhoff voltage law equation at mesh number 1. So at mesh number 1, if I start, maybe I start here lah. I have V 3 kilo, positive lah, but we have positive first, plus V 3 kilo plus V 4 kilo plus V 2 kilo plus 5. And we return back to our original place where we start, equals to 0. If you look here, we have actually these two can be combined. And if you have these two combined, you will have 7 kilo ohm over here at your left hand side. And you only need to have basically, if I expand this equation, it will be like this. 3 kilo times I1 plus 4 kilo also times I1 plus 2 kilo times I1 minus I2. Okay. And equals to negative 5. I put this 5 volts across, and this current I1 minus I2, where do I get it? From this junction. According to that junction, I have current I1 over here, and I have current I2 flowing that way, and I need to find what is the current over here. I is given by I1 minus I2, and this I basically contributed to the voltage drop across this 2 kilo ohm resistor. So that's why this 2 kilo ohm resistor is given by 2K I1 minus I2. And if you solve this part, okay, let's say for I1 we have 3 kilo plus 4 kilo, 7 I1, 7 kilo I1 plus this 2 kilo, means that we're going to have 9 kilo times I1 minus 2 kilo I2. So that's why we have this minus 2 kilo I2 and equals to negative 5. So that's for mesh number 1. For mesh number 2, again, we do the same procedure. In this mesh, we only have one element that have a voltage drop. Here I label, if the current is flowing that way, means that we're going to have a voltage polarity to be set up like that. So in mesh number 2, okay, I have, if I start from here, I start from here and go around the loop and return back to the origin place, I should have negative 5 plus V2K, okay, plus, sorry, minus 8 equals to 0. And if I put 5, negative 5 and 8 towards the other side, so I have V2K equals to 13. And V2K, okay, it's come from this current multiplied by this 2 kilo ohm. And looking at the current direction, basically it's in the opposite direction of the current that we got over here. Means that this is, if I try to find this is I is basically given by I2 minus I1. It's the in opposite direction, because maybe I put it as I prime lah. I prime. Okay. Here I have I pointing downwards. I here. I prime is the opposite direction of I. So just flip this equation. You're going to have negative, I2 minus I1. So that's why here we have negative 2 kilo I1 plus 2 kilo I2 equals to 13. And the rest of the solution is just a mathematic where you try to find, where you try to find what is the value of I1 and also I2. In this case, once you got I2, definitely you solve the value for IN, because I2 equals to IN. So later on, you have a look at this, all the solution of this. Just what I try to tell over here is the way how do we get all those equations. All right, now once you got your IN and RN, you can set up your Norton equivalent circuit using this circuit arrangement. So this is your IN in parallel with RN. And remember that we have open terminal A and B. Put our load resistor back and try to find what is the current at this load resistor, okay? And to get what is the voltage across this voltage across the resistor, you just apply simple Ohm's law, where once you find the current flowing through it, multiply it with the value of resistor, you will get what is the value of voltage drop or voltage across that load resistor. So that's for example number 1. Example number 2, you try to use Norton to find IO, and we try to find IN using node analysis. So here, IO is at this resistor, means that this is our open terminal, okay? Maybe you should label this A or B or vice versa. And if you look at the solution, we remove the open terminal first and label it as A and B. And for RN, what you need to do is you try to make this voltage source to be short circuit. It's basically at this part, okay? And we try to make this current source to be open circuit. Basically, it's here. It's here, open circuit and also short circuit. And you try to find RTH, or sorry, RN over here. Basically, RTH and RN is the same value. And looking at this, looking at the circuit arrangement, at the end, you will find your RN is equal to 800 in parallel with 200, okay? And in series with 40. Later on, parallel it with 50 ohm. So I need you guys to really have closely analyze the circuit. I leave you guys the work to analyze how do we find this equation for Rn. Maybe you can put it one by one or step by step. For example, here, how does these two considered as parallel? Okay. Okay. Look at the connection. If you look at this 800, at the end of 800 we have point A. Okay. At the end of the other side of 800 we have this point. Okay. Let's say this point is X. Look at this 200. The first side of 200, or at the end of this 200, we also have X, and the other side of 200, we also have A. Since if this is A, since we have wire over here, this is also considered as A. So that's why we can say that these two, 800 and 200, is considered as resistors connected in parallel, because both resistors is connected to the same terminal. And how about this, the others? Okay, the others I will let you guys determine by yourself. We finish with Rn. You also already know what is the value of Rn. Later on, what we're trying to do is we try to find IN using node analysis. And remember that to find IN, what you need to do is you try to short circuit the open terminal and label it as IN to be in that direction. You can also put it in the other way around, or in the opposite direction. But remember, if you put it that way, please remain, please remain that direction towards the end of your analysis, as well as please be more selective in terms of pointing the current direction. Means that you need to make the direction to be as easy as possible for you to analyze your parameters. For example, in this case, IN is labeled to be in that direction according to the question earlier. So put the direction according to the question. So later on, if you try to analyze the current, and it's easy for you. Okay, now node analysis. So we have one. This node is considered the same node. Okay, V1 also X is considered the same node because this is just a wire. Another node, we have V2 over here. So at node V2, okay, considering this is our node V1 and this is our reference node. From V1 to reference node, we have 50 volts, means that V1, we don't need to calculate V1 because it's already given by 50 volts. What you need to do is you need to analyze at V2 later on, where at V2, okay, you need to have a look at the current coming in and current coming out. So current coming in, current coming out, or in other words, the direction of a current, you need to set up or you need to assign it earlier. So, and then remain the direction towards the end of your analysis. So in this case, we already assigned to be in that direction. So now we can set up the current Kirchhoff law at node V2. Looking at node V2, we have current coming in, which is I2, and current also I1 as current coming in. And I think also this 750 milliampere also coming in. So that's why we have I1, I2, and 700 milli as considered as sum of I in. Consider it as sum of I in. And I out, in this case, is I3. Okay, I3 and as well as basically this current. So here we have I3 as current coming out. Why not consider that branch here? Wait, I think there's a slight mistake in this solution, because if we see at the definition over here, no, the original question. Okay, at V2 we have this 200, means that we need to add this 200 as I4 over here, and IT plus I4 as our sum of current going out from that node. All right, for I1, it's very straightforward. Why is I1? Oh, okay, because I1 is at the top. Okay, V1 minus V2 divide by 800 for I1. For I2 is here, since this is V1, this is also V1 as well. So V1 minus V2 divide by this resistor. So for this is for I2. Okay. 700 milliampere current coming in. For this part, we have I3. I3 is given by okay. I see what is the problem now. Okay, now Okay, this is not I4. Okay, this is basically we try to remove it first. This is not I3. Okay, this is considered as I4. Current coming, okay, again, current coming into node V2 is these three elements, I1, I2, and I3. Current coming out from node V2 is only I4 in this case. I4. That's why this is incorrect. This is not I3 because I3 is current over here. Okay. I4 is given by V2 divided by 200. Then this is correct. Okay, that's the problem of this solution. This is incorrect, yeah? Please correct your notes. And once you express your current in terms of voltages, you try to simplify that equation, and at the end, you will end up with this equation. This is our second equation. And remember that we already know what is the value of V1. We can simply put it into this equation to get the value of V2. Okay. And looking at the circuit back, IN is basically current over here, current here. And to find what is current over here, you need to do, or you need to assess the KCL at point X, at this point, okay, at point X. At that point is that if I will draw it back, IN is here, and I2 going this way, and we have another current over here. This is the correct I3. This is wrong. This should be I4. Okay. Looking at this junction, we know that IN is given by I2 plus I3 because IN is current coming in, I2 and I3 is current coming out. So IN equals to I3. IN equals to I2 plus I3. We have I2 is given to by this equation, okay, and I3, okay, I3 given by V1 divided by 50. So here, maybe I write it back at the top here. I2 is given by V1 minus V2 divided by 40. This equals to IN. And plus, okay, for I3 is V1 divided by 50. Okay, and we have V1 considered as 50. 50 minus 66 divided by 40. And for V1, we have also 50 over here, plus 50 divided by 50. So this is 1, and you will end up with all these equations. Please have a look at, okay, this is for I2. Okay, all right. The answer is already written down here. So it's easy, I think. For I3 is 50 divided by 50 for the second part, and at the end you will get IN equals to 0.6 ampere. All right, for the last step, you draw back your Norton equivalent circuit, consists of current source in parallel with resistor, and put back your load resistor, 80 ohm load resistor, and try to find what is the current flowing here using current divider rule. Current divider rule here says that if you try to find the current over here, use this resistor, 40, divide by 40 plus 80 times the current flowing into those two branches. So here, the equation stated here is is solved using current divider rule. All right, any questions so far? Any question?
No.
Okay, I'll also leave you guys with two exercises, exercise 3 and exercise 4, concern about Norton theorem. And please have a look at those exercises. First, have a look at the example and also look at the exercises. You need, as usual, you need to submit the answer by this Friday, 20th of November. And I think that's all today because we already finished material up until theorem, circuit theorem, Thevenin and Norton already finished. For next topic, this is also important. Next topic is a first order, second order circuit, where we try to consider capacitor and also inductor in our circuit, in our DC circuit. For your information, the first order circuit and second order circuit is a bit tough and also not being included in test 1. One question will be coming from this topic, first order, second order DC circuit, in your final exam. So this topic will be asked in your final exam. One topic, one question, 25 marks over here. But for time being, please do revision up until week number 5. And if I have more information, if I can share more information, I will share more information on your test, the content of test 1. Okay, everyone clear about next topic and also what's will be asked in your test?
Yes.
Yeah.
Okay. Okay,
Yeah.
have a look at e-learning portal. Please get into your e-learning portal and I've uploaded some, what do you call it, important materials lah, for you to do revision and for you to have information about this course. You need to log in into e-learning portal. All right, as usual, you need to